Please subscribe to support the channel. You are not looking at space as it is today. You are looking at space as it was billions of years ago. And the crazy part is, you're doing that with light your eyes cannot even see. So let's break down how James Webb actually pulls that off, step by step. First thing, when you see a James Webb image, you're not just seeing a nice background for your phone. You're looking at light that left its source more than 13 billion years ago, right after the Big Bang. The universe was small, very hot, and packed with matter. As space expanded, the light traveling through it got stretched, like pulling apart a slinky. But we'll keep it simple. The color of that light slides from energetic ultraviolet down through visible and then past red into the infrared. By the time it reaches us today, that light is so stretched that your eyes cannot detect it at all. This is why Webb was built for the infrared and not for pretty visible colors. Its main camera, NIRCam, is designed to see wavelengths from about 0.7 microns up to around 5 microns. That is deeper into the infrared than Hubble could really handle. The result is simple. Galaxies that lived when the universe was only a couple 100 million years old, around 2 to 3% of its current age, show up clearly for Webb, but would basically be invisible or extremely hard for Hubble. So the obvious question is, how do you turn that stretched light into a number that tells you how far back in time you are looking? How do you move from "this looks very red" to "this is a universe at less than 300 million years old"? That is where redshift comes in. Astronomers describe how stretched the light is with a single number called redshift, written as Z. If a galaxy is at a redshift of about 1, that means the light has doubled its wavelength on the trip. If it is at a redshift above 10, the wavelength is more than 11 times longer than when the photon left the galaxy. At around redshift 14, like the record holder called JWST-Z14-0, you are seeing the universe when it was under 300 million years old. Here's the part that sounds wrong at first. A photon that left that galaxy has been traveling for more than 13 billion years, but because the universe has been expanding while that photon moves, the galaxy is not 13 billion light years away right now, in what cosmologists call co-moving distance. It is tens of billions of light years away. Some of these objects are over 30 billion light years in that sense. So when you hear redshift 10, 12, 14, that is not decoration. That is a timestamp on the history of the universe built into the light itself. Now you might ask, okay, we have this nice idea of redshift, but how does Webb actually measure it? How do you move from a fuzzy dot in a deep image to a very precise redshift number and a solid age? Webb does this with two main instruments that work together, NIRCam and NIRSPEC. First, NIRCam, the near-infrared camera, takes the deep, detailed images you see online. It uses multiple infrared filters. You can think of them as tinted windows that only let through a narrow band of wavelengths. When astronomers measure how bright a galaxy is in each filter, they can already estimate a redshift based on its color pattern. These are called photometric redshifts. They're fast and good for finding candidates. But estimates are not enough if you want to be sure. That's where NIRSPEC steps in. Instead of just measuring total brightness in a filter, NIRSPEC spreads the light out into a full spectrum. This spectrum shows thin features called emission and absorption lines created by elements like hydrogen and oxygen inside the galaxy. Astronomers know the original wavelengths of those lines, so when Webb sees them shifted into the infrared, it can calculate exactly how much they moved. That gives a precise spectroscopic redshift, often nailed down to a tiny fraction of a percent. This is the core method in big programs like JADES, the JWST Advanced Deep Extragalactic Survey. First, NIRCam scans a patch of sky for faint red galaxies that might be very distant. Then they point NIRSPEC at those candidates. confirm which ones are actually at high redshift, and measure not just distance, but also things like how many heavy elements they contain and how quickly they're forming stars. That's how a faint smudge becomes this galaxy is at redshift 14.3 and forming stars at a furious rate. But you're probably wondering, are these just a few lucky finds, or are there whole crowds of galaxies from this early era that we were simply blind to before Webb? To answer that, Webb does ultra-deep observations. Instead of scanning huge areas, it stares for a long time at a tiny piece of sky. One of the famous examples is its first deep field, a galaxy cluster called SMACS 0723. If you hold a grain of sand at arm's length, that's about the size of the region Webb zoomed in on. In that tiny patch, it found thousands of galaxies, layered at different distances, some fairly close in cosmic terms, but many from the first billion years after the Big Bang. These deep fields are not random pretty shots, they're statistical tools. By counting how many galaxies show up at each brightness and redshift, astronomers can work out how common galaxies were at different times, how fast they grew, and how quickly they were forming stars. Webb pushes this census out to redshifts around 10 to 14, much farther than Hubble could reliably reach, which means we now see the galaxy population in an era that used to be almost dark to us. Still, there's one last step. You might ask, how do you go from we detected some photons to we know this galaxy lived X hundred million years after the Big Bang? What's the full pipeline? Here's how it works, in simple steps. First, NIRCam detects a faint object in several infrared filters. Maybe the galaxy is totally absent in the bluer filters and then suddenly appears only in the redder ones. That pattern is a big red flag that it might be a very distant galaxy. The reason is something called the Lyman break. Hydrogen gas in or around a galaxy blocks light above a certain energy in the ultraviolet, so the galaxy's brightness drops sharply at that wavelength. As the universe stretches the light, that sharp drop gets shifted into the infrared. When astronomers see that drop land between specific filters, they can estimate the redshift. Then they select the best candidates for near-spec or another spectrograph. Once they get a clean spectrum, they look for known emission lines from hydrogen, oxygen, or hydrogen alpha that have been shifted into the infrared. From the amount of that shift, they calculate the redshift very precisely. After that, the last piece is cosmology. Given a redshift and a specific model of how the universe expands over time, they convert that into a look-back time and an age of the universe at that moment. So they can say, in plain language, this galaxy existed about 250 million years after the Big Bang. That is how a few stretched photons turn into a point on the timeline of cosmic history. And here's the part that sets up everything else in the story. Once Webb starts filling that early timeline with real galaxies, with real masses and star formation rates, a new question appears. Are there more galaxies and brighter galaxies in that early universe than our best model said there should be? And if the answer is yes, what exactly is broken? The galaxies, the models, or our whole picture of how fast the universe grows structure? Here's where Webb stops being just impressive and starts being uncomfortable, because now you're not just seeing early galaxies, you're seeing galaxies that, on paper, were not supposed to be there yet. Start with the current distance champ, Jade's GS Z140. This thing existed less than 300 million years after the Big Bang, long before the Milky Way, long before the Sun. Webb's NIRCam picked it out in the Jade survey. Then, near-spec locked in a redshift of 14.32 with small error bars on top of that, making it the most distant confirmed galaxy we know right now. Translate that into normal language, the light has been traveling for about 13.4 billion years. The universe back then was a toddler, and yet this galaxy is already bright, actively forming stars, and spread over more than 1,000 light years. Not a tiny flicker, but a serious system. Standard galaxy formation models did not predict the whole population of galaxies this bright, this early. That's the first alarm bell. You point Webb at a deep field, and instead of a few rare oddballs, you start getting a list of them. You could still say, okay, maybe that one is a fluke, some weird overachiever. But then you hit the next case, Glass Z12. Glass Z12 showed up in early JWST glass data, first as a very bright high redshift candidate in NIR CAM images, later confirmed spectroscopically at a redshift of 14.32. So again, you're looking only about 355 million years after the Big Bang. Here's the part that really matters. ALMA and JWST both see a strong emission line from doubly ionized oxygen, and even hydrogen alpha and other lines. That means this galaxy has already run several rounds of star formation. Massive stars have formed, lived, exploded, and dumped heavy elements like oxygen into the gas. And all of that has happened a little more than 300 million years after everything started. So you're not just seeing early galaxies, you're seeing chemically evolved galaxies, star factories that have been running long enough to pollute their surroundings. That is fast, much faster than a lot of models we're comfortable with. Maybe you think, fine, there are a couple of extreme objects, but we already knew about distant galaxies before Webb, right? What about the old champion, GN-Z11? GN-Z11 was the big deal in the Hubble era. First measured at around redshift 11, then Webb came in with near spec and nailed it down to 10.6034, with tiny error bars on top of that, making it the most distant confirmed galaxy we know right now. Translate that into normal language, the light has been traveling for about 13.4 billion years. The universe back then was a toddler, and yet this galaxy is already bright, actively forming stars, and spread over more than 1,000 light years. Not a tiny flicker, but a serious system. One dramatic galaxy, or even a handful, might still be something you can explain away. But the real problem shows up when you stop looking at single objects and start counting. How many of these high redshift galaxies are there per unit volume, per unit brightness? That's where the Hubble Ultra Deep Field, reobserved with Webb, comes in. Teams using JWST's NIR CAM and the HUDF have found a steep rise in the number of galaxy candidates at redshift above about 9.5 or 10, and quite a few of them are surprisingly bright. That brightness translates into significant stellar masses, already in place only a few hundred million years after the Big Bang. If you take these counts at face value and convert the light into stellar mass in the usual way, the total stellar mass density at those early times comes out higher than what standard ΛCDM-based galaxy formation models would have predicted, assuming normal star formation efficiency. In plain terms, you get too many stars too early in too many galaxies too early. So what does that do to ΛCDM, the standard model of cosmology that has been working very well from the cosmic microwave background up to galaxy surveys today? One or two galaxies at around redshift 12 could be blamed on bad modeling, lensing magnification, dust tricks, or just rare statistical flukes. But when you see hundreds of candidates across independent surveys like JADES, GLASS, and HUDF pointing in the same direction, you no longer have an easy escape route. You're pushed into a set of hard options. Maybe galaxies in the early universe formed stars much more efficiently than our recipe said they could. Or maybe more of the gas collapsed rapidly into stars with less waste. Or maybe we're missing something deeper. Maybe our assumptions about dark matter, dark energy, or even the initial conditions from the Big Bang are slightly off, changing how fast structures grow at the highest redshifts. There's also the conservative possibility that some of the early mass estimates are biased high, that some objects are lensed or contaminated, and astronomers are absolutely checking for that. They're refitting the data with different assumptions, looking for hidden lensing, and comparing independent catalogs. But even with more cautious modeling, the overall story doesn't just vanish. The early universe still looks busy. So no, Webb has not killed ΛCDM, but it has put it under non-trivial stress. The model can be made to survive, but you have to work harder, tune parameters more tightly, or even consider extra ingredients like early dark energy or modified small-scale physics. And that leads to the next question you have to face. If these galaxies exist in such numbers this early, how massive are they really? And are we already seeing full-size galaxies, close to Milky Way mass, less than a billion years after the Big Bang? Because if that's true, the tension with our growth curves doesn't just get interesting, it gets severe. Here's the part that really makes theorists sweat. Because now you're not just counting early galaxies, you're asking how heavy they already are, and the answer comes back way higher than anyone was comfortable with. At redshifts around 7 to 10, so within the first 700 to 800 million years after the Big Bang, some JWST studies are finding galaxies whose stellar masses are on the order of 10 billion to 100 billion suns. That's already in the same ballpark of the Milky Way's stellar mass, but packed into a much younger universe. In simple terms, by the time the universe isn't even 1 billion years old, you're already seeing systems that look like mid-sized to giant galaxies, not tiny test versions. These objects are not faint edge cases. They are bright, strongly star-forming galaxies that stand out in Webb's deep images and spectra. To build something that massive, that fast, you need huge amounts of gas to fall into dark matter halos, cool, fragment, and turn into stars very quickly. The timeline gets tight. You do not have 13 billion years to grow slowly. You have a few 100 million years to go from almost nothing to tens of billions of suns and stars. So then you take the next logical step. You add them up. You do not just look at single galaxies. You integrate over the whole population and ask how much stellar mass is already in place per unit of volume of space at these early times. When astronomers do that with JWST data, they estimate something called the stellar mass density. That is just a fancy way of saying if you take a big cube of the universe at some early redshift and sum up all the stars inside it, how heavy is that box on average? The answer that comes out of several Webb surveys is that at very high redshift, this stellar mass density can be several times higher than what standard ΛCDM-based galaxy formation models predicted using normal rules for star formation. You can say it very bluntly. By a few 100 million years after the Big Bang, the universe seems to have already spent more of its gas budget on stars than our models gave it permission to. That is not a cosmetic problem. That directly hits how fast structure is allowed to grow, how quickly dark matter halos assemble mass, and how efficiently those halos can cool gas and turn it into stars without breaking other constraints. Then you look at how these galaxies are still behaving right now in that early frame, and it gets even intense. Many of the massive JWST galaxies show star formation rates of tens to hundreds of solar masses per year. Compare that to the Milky Way today, which turns maybe 1 to 3 suns worth of gas into new stars each year. These early galaxies are running star factories at rates tens or even hundreds times higher, and they're doing it in a universe that is still under a billion years old. Webb spectra back this up with very concrete signals. You see bright nebular emission lines from hydrogen, oxygen, and other elements, which are directly tied to how many hot, young, massive stars are being formed. Programs like JADES and GLASS use the strengths of these lines combined with the continuum light to compute star formation rates. So when someone says this galaxy is making 100 suns per year at redshift 10, that is not a guess from a pretty color picture. It comes from detailed spectroscopy and physical calibrations. At this point, you have 3 related facts staring at you. Galaxies that are too massive, too early, with star formation that is too intense for comfort. So naturally, people start asking, is the underlying cosmological model slightly off? And can one tweak fix multiple headaches at once? One idea on the table is something called early dark energy. The basic thought is this. Maybe in the first few 100,000 to few 100 million years, there was an extra component that behaved a bit like dark energy, changing the expansion rate of the universe at early times. That same kind of tweak has already been explored as a way to reduce the Hubble tension, the mismatch between the expansion rate measured locally and the value inferred from early universe data. In simple terms, if you change how fast the universe was expanding back then, you change how quickly dark matter halos can grow and merge. Slightly different early expansion means slightly different timing and abundance of massive halos at high redshift. That, in turn, might make it easier to get big galaxies earlier without wrecking the very tight constraints from the cosmic microwave background and other probes. No one is claiming problem solved yet, but JWST's massive early galaxies are now being actively used as a stress test for these new physics ideas. If your early dark energy model cannot produce enough big halos by redshift 8 to 10, it's in trouble. Of course, there's always the conservative reaction you hear whenever a result looks extreme. Maybe the stellar masses are overestimated. Maybe dust is making galaxies look older or more massive than they are. Maybe some of these sources are boosted by gravitational lensing, making them appear brighter and hence more massive than their true intrinsic values. Maybe our assumptions about the stars inside these galaxies are off. Astronomers are not ignoring that. They are refitting the spectral energy distributions with different models for star formation history and dust. They are checking high-resolution images for signs of lensing, like arcs or multiple images. They're comparing independent surveys that use different filters, different analysis codes, and different teams. Some early claims of ultra-massive galaxies have already been revised downward once better data came in, or once more careful modeling was done. But here's the key point for you. Even after you throw out the most extreme early claims, even after you push the assumptions in favor of lower masses and lower star formation rates, the universe in the first billion years still looks very active. The tension can be softened, but it doesn't evaporate. You still end up with more stellar mass, more bright galaxies, and more star formation at high redshift than the simplest versions of our models were building before Webb flew. So the message at the end of this section is direct. Even in the most generous, conservative version of the old picture, the early universe is still building galaxies with surprising efficiency. And if it can do that fast and hard, that raises a new question downstream. If stars and galaxies were turning on this quickly, how soon did all that light start punching holes in the neutral hydrogen fog that filled the young universe? And did Webb just catch that process starting earlier and moving faster than we thought it would? Right now, the big question isn't just how many early galaxies are there, it's what did all that new light actually do to the universe around it? Did it sit there quietly, or did it tear the early universe open? About 300,000 years after the Big Bang, the universe cooled enough for free electrons and protons to hook up into neutral hydrogen. From then on, for hundreds of millions of years, space is filled with this neutral hydrogen fog, and neutral hydrogen hates high-energy ultraviolet light. It absorbs it, especially the photons strong enough to rip electrons back off those atoms. So even if the first stars switch on, their hardest UV light doesn't travel very far. It gets soaked up. The era when that changes is called the epoch of reionization. That is the phase when the first generations of stars and galaxies pump out so much energetic UV light for so long that they blast that neutral hydrogen apart again, turning it back into an ionized plasma and making the universe transparent to UV. Before Webb, the rough textbook timeline was simple and safe. Reionization starts somewhere around 400 million years after the Big Bang and finishes by about 1 billion years after. The open questions were, who did the heavy lifting, when exactly did it start, and was it slow and smooth or fast and patchy? Webb is going straight after those questions by looking not just at how many galaxies exist, but at what their light is doing to the gas between them. One of the most striking examples so far is a galaxy called JWST Z13-1, sitting at a redshift of about 13. That means you're looking at it roughly 330 million years after the Big Bang, well inside what used to be the fog should still be pretty thick territory. In Webb's data, this galaxy shows strong hydrogen features that point to a region of gas around it that is already highly ionized. In plain language, JWST Z13-1 looks like it is carving a clear bubble in the neutral hydrogen much earlier than expected. That is a problem for the old slow picture, because if galaxies at redshift 13 are already blowing big holes in the fog, then serious reionization activity must have started earlier than those 400 million year safe estimates. You can phrase it like this for your viewers. We thought the fog would still be mostly unbroken. Instead, we are already seeing harsh UV beams punching tunnels through it. To understand how Webb can say that with any confidence, you have to look at the main tools it uses: hydrogen emission lines. Whenever young, hot stars flood their surroundings with UV light, they ionize hydrogen atoms. Electrons get kicked free, then they fall back down into lower energy levels and emit photons at very specific wavelengths. Those show up as bright emission lines with fixed rest frame colors. Two of the most important ones are Lyman alpha in the ultraviolet and hydrogen alpha in the red part of the visible spectrum. In the very early universe, at redshifts between about 10 and 14, both of those lines get dragged far into the infrared by cosmic expansion, right into the wavelength range Webb's instruments like NIR-SPEC and MIRI are built to capture. By measuring how strong those hydrogen lines are, how much they are shifted, and how much of them seems to be absorbed or scattered away by neutral hydrogen along the path, astronomers can figure out two key things. First, how ionized the region around the galaxy is. Is it sitting in a mostly neutral fog or inside a big bubble of already ionized gas? Second, how powerful that galaxy is as a UV engine, how many ionizing photons it is likely pumping into the intergalactic medium. That is how a single object like Jade's GS-Z13-1 can be caught in the act of clearing a local bubble in the cosmic fog. You're not guessing. You are reading hydrogen's neon sign in the infrared and seeing how much blank space it has already burned through. But obviously, one dramatic galaxy is not enough. The bigger question is, who did most of the work overall? Was the universe reionized by huge numbers of small, faint galaxies that you barely see? Or by a smaller population of bright, extreme monsters that punch huge holes quickly? This is where Webb's deep surveys really matter. JADES, SEERS, and similar programs are finding two things at the same time: swarms of faint galaxies going down to very low luminosities, and also a set of surprisingly bright compact galaxies with extreme UV output and very high star formation rates. The current picture, based on these counts and on how much light each population produces, is that the faint galaxies probably dominate the total ionizing photon budget. There are so many of them that their combined output adds up. But the bright galaxies are not irrelevant, far from it. They seem to play an outsized role in creating the biggest, earliest ionized bubbles. You can think of it this way. Reionization is a team sport, but some players are absolutely the star scorers. Those bright, compact galaxies, sometimes with active black holes inside, can rip open large chunks of the neutral hydrogen much faster than average. When you put all of this together, the timing starts to shift. Webb is seeing ionized bubbles and strong hydrogen emission at redshifts above 10, even nudging into the 12 to 13 range. That pushes cosmologists to rethink the old timeline. If galaxies are already clearing bubbles that early, then reionization probably started earlier than many models assumed, maybe closer to 250 or 300 million years after the Big Bang, instead of waiting till 400 or later. It also suggests that reionization is not a smooth global fade from opaque to transparent, it's patchy and fast, with ionized bubbles growing around early galaxies and then overlapping, leaving behind neutral pockets that survive longer in quieter regions. On top of that, the efficiency with which early galaxies leak ionizing UV photons into the intergalactic medium has to be recalibrated. They might be better at letting that radiation escape than people assumed, especially the compact, low-mass systems. So the punchline in this section is simple. Webb did not just give us a sharper picture of the epoch of reionization, it changed the schedule. The universe seems to have lit up the fog earlier, more aggressively, and in a more uneven way than the clean, slow cartoon version many people had in mind. And here's where the tension ramps up again, because once you accept that reionization is driven by intense UV from very young galaxies, another question shows up. If all that energy is blasting the gas around them, what is powering those galaxies so fiercely from the inside? Are we just dealing with normal stars turning on? Or are there signs that right from the start, there were monster stars and growing black holes dumping even more energy into the game than we expected? There's a bigger problem hiding under everything we've said so far. And it's this: if the early universe was already full of big, bright galaxies, what was sitting in their centers? Because by less than 1 billion years after the Big Bang, we already see quasars powered by black holes that are hundreds of millions, even billions of times the mass of the Sun. Starting from normal black holes made by dying stars, maybe 10 to 100 solar masses, and letting them eat at normal rates, you simply do not reach 1 billion suns that fast. You run out of time. That growth curve just doesn't fit. This is one of the core puzzles JWST is now attacking from several directions. It's not just counting galaxies, it's giving us hints about how you might build those monster black holes early, by changing the starting conditions and by showing us that black holes and young galaxies are not quiet passengers. They're active, messy, and sometimes completely unbound. One light of evidence comes from chemistry, which sounds boring at first, but it's actually a very sharp tool. In some distant galaxies, like one labeled GS3073 in JWST studies, astronomers see strange ratios of nitrogen to oxygen in the gas. Those ratios are hard to produce with normal mixes of stars like the ones in the Milky Way today. One clean interpretation is that the early universe hosted a short-lived generation of monster stars, stars hundreds of times the mass of the Sun, burning hotter, fusing elements along different paths, and dumping a lot of nitrogen relative to oxygen when they die. You can explain this to your viewers very simply. The gas in these galaxies is like a forensic report. There's too much nitrogen compared to what normal stars would leave behind. That points to a brief era where absurdly massive stars dominated, lived fast, died violently, and in some cases probably collapsed almost directly into very heavy black holes, seeds in the range of thousands, maybe tens of thousands of solar masses instead of just 10. Those heavier seeds are dramatically easier to grow into the supermassive black holes we see by redshift 6 or 7. You are no longer trying to turn a pebble into a mountain in record time. You're starting with a boulder. But chemistry is only one piece. Webb is also finding direct signs that black holes in the early universe were already active and sometimes completely hidden. A whole new class of objects has popped up in JWST data. People often call them little red dots. They're compact, very red sources at high redshift. In at least one detailed case, a galaxy nicknamed Virgil, the object looks like a pretty normal star-forming galaxy in rest frame visible in ultraviolet light. But in JWST's mid-infrared, it suddenly lights up as something far more intense. That mid-infrared glow, combined with its compact size and spectral features, matches what you would expect from a heavily obscured, overmassive black hole feeding behind thick dust. That tells you several important things at once. First, supermassive black holes were already active, already accreting and heating their surroundings, perhaps as early as 800 million years after the Big Bang, not just in the later universe. Second, many of them might be almost invisible in optical surveys, buried inside dusty galaxies, and only show their true power in the infrared. Third, the black hole may actually be overmassive compared to the galaxy's stellar mass, meaning the black hole can grow faster than the rest of the galaxy, not just in sync with it. That hits an older, cleaner narrative pretty hard. For years, the standard line was that galaxies and their central black holes grow together, roughly tracking each other with simple scaling relations connecting black hole mass to galaxy mass. Webb is now showing you cases where the black hole might be out ahead, punching well above what that simple picture predicts. And as if that were not enough, there are signs that black hole dynamics themselves were violent. One of the most dramatic examples is a candidate runaway supermassive black hole seen in Hubble and followed up with Webb and other telescopes in a system nicknamed the cosmic seahorse or cosmic owl, depending on the interpretation. You're looking at a black hole with a mass of around 10 million suns, moving at roughly 2.2 million miles per hour, leaving behind a narrow trail of newborn stars stretching about 200,000 light years. The best explanation is that a three-body interaction between black holes in merging galaxies slingshotted this one out of its original galaxy at high speed. For your audience, you can put it in plain terms. Theorists predicted that in complex mergers, one black hole could get kicked out and fired through space like a cosmic bullet. But seeing such a clean, long tail of star formation behind a runaway candidate is strong evidence that even in the young universe, black holes were not politely sitting in galactic centers. They were merging, kicking, ejecting, and stirring up gas on enormous scales. Now, tie all of this back into galaxy growth. If the early universe really had a brief era of monster stars, those would leave behind heavy black hole seeds. In young, extremely gas-rich galaxies, those seeds could feed rapidly, growing orders of magnitude in mass while the galaxy is still assembling. As they grow, they emit huge amounts of energy in radiation and sometimes in jets, which heat or blow out surrounding gas or compress it and trigger new star formation in certain regions. That process, called feedback, means the black hole is not just a passive observer, it is a control knob that can regulate how fast the galaxy turns gas into stars. Blow too hard and you can shut star formation down in the center. Heat or stir the gas in the right way, and you can push gas into dense clumps and get new starbursts. When black holes merge or when one is kicked out, you can strip gas, distort galaxy shapes, and fling metals out into the surrounding intergalactic medium. So the new picture looks very different from the old, neat, slow story. Webb is pushing us toward a view where from very early on, you have three things running at high speed together: intense star formation, rapid black hole growth, and strong feedback tying the two. Monster stars create heavy seeds. Dense early galaxies feed them, and their energy output then reshapes how those galaxies evolve and how they light up the cosmic web around them. And once you accept that, another uncomfortable question appears. If black holes and feedback are this strong this early, and if galaxies are this compact and structured at high redshift, how fast did ordered galaxy shapes, disks, clumps, and rotations appear? Because if even the baby pictures of galaxies already look sharpened and organized, then the universe was not just busy, it was efficient in building structure from almost the very beginning. Here's the next twist. When you zoom in on these early galaxies with Webb, they don't look like fuzzy, formless blobs. A lot of them already look organized, and that's a problem if you thought structure should take its time. At redshifts around 6 to 10, so within the first billion years, Webb's infrared resolution is sharp enough to actually resolve shapes over just a few thousand light years. And what you see over and over is not just chaos. You see hints of disks, you see clear clumps, you see light stretched out in ways that look like rotation and flattened structures, scaled down compared to the Milky Way, but very much like real galaxies, not test versions. These systems are tiny in size, but they're not shapeless. Then you look closer at the bright spots inside them, and things get even more intense. Instead of smooth light, you see big, clumpy star-forming regions, often a few hundred light years across, sometimes larger. For comparison, one of the famous star-forming regions in our own Milky Way, something like the Orion Nebula, is only a few dozen light-years across. These early clumps are like supercharged star factories, whole neighborhoods of star formation crammed into galaxies that are themselves only a few thousand light-years wide. That tells you the gas inside these baby galaxies is fragmenting into very dense pockets very quickly, turning into stars in huge batches. Star formation is not gently spread out, it is focused into giant, bright clumps, and Webb can literally pick those clumps apart in the infrared. But it is not all neat disks and isolated clumps. A lot of Webb's high redshift galaxies look disturbed. You see stretched out tidal tails, double or offset bright cores, asymmetric shapes that do not match a calm rotating disk. Those are classic signatures of mergers. Two or more galaxies in the process of colliding and blending. Given how small the universe was at those times and how dense the environment was, frequent mergers are expected in theory. But now, you are watching them in action, less than a billion years after the Big Bang. This fits the basic hierarchical structure formation story, where small things form first and then merge to build bigger structures. But the details matter, because some of these systems are already surprisingly massive for their size, and the mergers look violent and common. You are seeing galaxies being shaken, fed, and reshaped in real time at cosmic dawn. Now talk about size versus mass, because this is where the numbers get uncomfortable again. Many of these high redshift galaxies are physically small, maybe 3,000 to 6,000 light-years across, compared to the Milky Way's roughly 100,000 light-year diameter. So in absolute terms, they are dwarfs. But when you estimate their stellar masses, they can carry hundreds of millions to tens of billions of solar masses and stars. That combination, small size but relatively high mass, gives you galaxies that are compact but beefy. Their stars are packed into a tight volume, making their average densities high. They don't sit cleanly on the scaling relations we use for galaxies in the nearby universe, where size and mass follow a smoother trend. At high redshift, the relation is shifted and the scatter looks bigger. Simply put, young galaxies are denser and more compact than you might expect if you just rolled back the clock on today's galaxies. And Webb is not just seeing this once or twice. It's a repeated pattern across multiple fields and surveys. Tiny systems with obvious clumps, small disks that are already rotating, double nuclei that scream mid-merger, high surface brightness cores that suggest intense star formation or central black hole activity in a very small region. The early universe is not a featureless fog with vague blobs slowly coalescing. It's a crowded, structured environment where ordered shapes and disturbed morphologies coexist very early. The implication is direct. Structure forms fast. You don't need billions of years to organize gas into disks, clumps, and rotating systems. Under the conditions at cosmic dawn, with high gas fractions, strong gravity, and compact dark matter halos, and frequent interactions, the universe can move from first light to recognizable galaxy structures in just a few 100 million years. That should raise a flag in your head, because if galaxies are already this organized, this compact, and this disturbed by mergers at high redshift, then the internal physics has to be running very hard. You have strong gravity, intense cooling, rapid star formation, and feedback all happening in small volumes. And that leads straight to the next pressure point. If structure, metals, and stars are building up this quickly, what does that say about the chemical state of the early universe? How fast did it go from almost pure hydrogen and helium to gas laced with heavier elements and dust that can reshape how galaxies grow and how we see them? Right now, the big question is not just how many early galaxies there are or how massive they are, it's what they're made of, because that tells you how many generations of stars have already lived and died, and how fast the universe went from clean to dirty. Start with the basics. In astronomy, metals doesn't just mean iron or gold. It means anything heavier than helium. Oxygen is a metal. Carbon is a metal. Nitrogen is a metal. All of that. Right after the Big Bang, the universe is almost chemically pure. Just hydrogen, helium, and a trace of lithium. No carbon for planets, no oxygen for water, no iron for cores, nothing. Every heavier element has to be forged inside stars, and then thrown back out into space when those stars explode or shed their outer layers. So if you look at a galaxy 500 million years after the Big Bang, and you already see metals in its gas, that means at least one full generation of stars has already formed, burned, and died. In some cases, it means several generations have come and gone. That's why Webb's chemical fingerprints are such a big deal. They turn light into a history of how fast the universe polluted itself. Webb gets those fingerprints mainly through near-spec. When gas in a galaxy gets hit by strong radiation from young stars, atoms like oxygen, nitrogen, and sulfur light up at very specific wavelengths. Near-spec spreads the galaxy's light into a spectrum and lets you measure the strength of those emission lines. From their relative strengths, astronomers can infer the metallicity, basically what fraction of this gas is heavy elements compared to hydrogen. Here's the key part. Webb is measuring those metallicities at redshifts above 7, 8, 10, deep into cosmic dawn. Some of those early galaxies already show clear non-zero metallicity, not just a tiny trace. That means they are not truly first-generation systems. They're second wave or later, built from gas that has already been enriched by earlier stars. In other words, by the time we can see them, the chemical clock has already been running for a while. On top of that, there's dust. Dust is made from heavy elements, tiny solid grains of things like carbon compounds and silicates. You can detect dust in a couple of ways. One is reddening. Dust scatters blue light more than red, so galaxies with dust look redder than they would from stars alone. Another is the infrared glow. thus absorbs high-energy photons and re-emits that energy at longer infrared wavelengths. Webb is extremely sensitive to that infrared continuum, so it can pick up dusty galaxies very early. This matters because dust changes how we interpret everything else. If you ignore dust, you might think a galaxy is old and dead just because it looks red, when in reality it is young and forming stars like crazy behind a dust screen. Correcting for dust usually pushes the star formation rates up, so every time Webb shows you a red, compact galaxy at high redshift, there's a follow-up question. Is it red because it's full of old stars, or red because it's packed with dust? The answer affects how fast you think stars have been forming and how quickly metals and dust themselves have built up. Now flip the logic. Instead of looking for enriched, dusty galaxies, you can hunt for the opposite. Systems that look almost chemically pristine. The very first generation of stars, often called population 3, would have formed out of metal-free gas, just hydrogen and helium. Those stars are expected to be very massive, very hot, and very short-lived, and they would leave distinctive signatures in the spectrum of their host galaxies, like extremely blue colors and peculiar line ratios. Webb has not yet given us a clean, undisputed detection of a pure population 3 star cluster, but some targets are getting close. JADES and other deep surveys are actively searching for galaxies with extremely low metallicity and very blue spectra, with almost no dust. When they find a candidate, they throw every spectroscopic tool they have at it to see whether the line ratios and continuum shape really point to near pristine gas and a top-heavy, very hot population of stars. Even if those systems still show tiny traces of metals, they're giving us the tightest constraints yet on how long truly metal-free star formation could have lasted. Put all of this together and you get a clear message. The timeline for chemical evolution in at least some regions of the universe is compressed. You go from pure hydrogen and helium to gas that already carries oxygen, nitrogen, carbon, and dust in just a few 100 million years. In some galaxies, metallicities climb to a decent fraction of the sun's value surprisingly early. That means multiple generations of stars have already cycled through, exploding, enriching, and mixing the gas in a very short window of time. That has a direct impact on everything else in your story. Metals and dust make gas cool more efficiently, which makes it easier to fragment into small clumps and form more stars. They also change how radiation moves through galaxies, affecting feedback and reionization. So once metals and dust show up this early, you are not just tracking chemistry, you are changing the rules of further galaxy growth. And here's the next pressure point that it creates. If metals, dust, structure, and black holes all ramp up this quickly, then the dark matter scaffolding that holds everything together has to be in place fast too. So the obvious next question is, what does JWST's early galaxy census say about the dark matter halos and filaments underneath? And are we starting to see cracks in our assumptions about the cosmic web itself? Here's the part a lot of people skip, but you can't, because if these early galaxies are real, then the invisible scaffolding underneath them has to be there too, and that means dark matter is under the microscope. Think of it this way. Every galaxy you've heard about so far, every JADES object, every glass candidate, is sitting inside a dark matter halo, a big invisible clump of mass whose gravity pulls gas in and lets stars form. In the standard ΛCDM picture, we know how many halos of a given mass should exist at each time. Small halos form first, then they merge into bigger ones. And the abundance of halos as the universe ages is something we can predict and match to simulations. So if JWST tells you there are more bright galaxies at high redshift than expected, it's really saying there might be more massive halos earlier than we thought there should be. So you ask the next question. How big do those halos have to be to host the luminous galaxies Webb is actually seeing at redshift above 10? You take the brightness, you estimate the stellar mass, you make reasonable assumptions about how efficiently a halo can turn its gas into stars, and you back out a halo mass. When you do that for a whole sample, you end up needing a lot of halos in the 10 billion to 100 billion solar mass range already in place when the universe is only a few 100 million years old. That is a strong demand on your dark matter model. ΛCDM says you can get those halos, but they should still be rare. JWST is hinting they might be less rare than the simplest versions of the model we're expecting. Then you look at how those galaxies are arranged on the sky in deep fields, and it gets even more interesting. Even with tiny patches of sky, Webb is starting to show hints of structure, not just random isolated points. You see chains and groups of galaxies that line up in ways that look like early filaments, proto-cosmic web strands already forming when the universe is still under 1 billion years old. It's not yet the full large-scale structure map you get at low redshift, but it's a clear sign that clustering and web-like patterns are in place fast. That matters because the cosmic web is basically dark matter's fingerprint on large scales. Gas and galaxies are just tracing the dark matter skeleton. So if filaments and dense knots are already visible at high redshift, it tells you that dark matter collapsed into a web very quickly. Again, that doesn't contradict ΛCDM outright, but it pushes you toward the more extreme end of what the model can comfortably allow. Now zoom in on a different kind of dark matter test, small-scale structure. There are versions of dark matter, like warm dark matter or more exotic models, that smooth out the smallest halos. They act like a built-in blur filter, suppressing the formation of very small dark matter clumps. That in turn would reduce the number of small, faint galaxies at high redshift. JWST is now finding a lot of faint galaxies, plus evidence for significant structure even on fairly small scales very early on. That puts pressure on those alternative dark matter models, because if you erase too much small-scale power, you simply can't get the number of little galaxies and early halos that Webb seems to be revealing. So you end up in a slightly uncomfortable middle ground. Dark matter as a concept is not in danger. ΛCDM still matches the microwave background, large-scale structure, and a ton of other data. But JWST is forcing you to tighten the screws. There's less room for dark matter to be warm or fuzzy or heavily self-interacting in a way that kills small halos. There's less room for sloppy, low-resolution simulations that underproduce early structure. You need better simulations with higher resolution, better baryonic physics, and more realistic feedback to see if a vanilla ΛCDM universe can really build the halo population JWST is apparently seeing. That's the key message you want to land here. Webb does not kill dark matter, it sharpens the test. The basic idea of a dark matter web holding galaxies is still standing, but the edges are fraying. The early universe looks more clumpy, more structured, and more active than a lot of pre-JWST models predicted. And that means cosmologists are now rerunning their codes, tweaking parameters, and in some cases exploring slightly modified dark matter scenarios to see what survives. And once you realize the dark matter scaffolding is this tightly constrained, you run straight into another major tension point, because one of the biggest fights in cosmology right now is about how fast the universe is expanding, and JWST's early structure is now being dragged into that argument too. So the next question is simple and sharp. If the early universe is this busy, does that help fix the Hubble tension, or does it make the story even harder to tell with just one clean expansion history? Here's the part where all of this stops being just cool images and slams into the core of cosmology. Because if the early universe is busier than expected, that connects straight to a fight people are already having about how fast the universe is expanding right now. First, you need the basic problem on the table, the Hubble tension. When you measure the expansion rate of the universe, the Hubble constant, using the local universe, nearby supernovae and galaxies, you get a value around 73 kilometers per second per megaparsec. That means every extra megaparsec of distance adds about 73 kilometers per second of recession speed. But when you infer that same number from the early universe using the cosmic microwave background and the ЛCDM model, you get closer to 67. Those two numbers are far enough apart that with current error bars, they don't overlap. That isn't just a little disagreement, that's a real tension between late universe and early universe measurements. Now plug JWST into this. Why would early galaxies matter for a fight about the expansion rate today? Because the abundance and growth of structure at high redshift is sensitive to the whole expansion history. If the universe expanded a bit differently in its first few 100,000 to few billion years, you would change how fast dark matter halos formed, how quickly gas could fall in, and how many massive galaxies you'd expect to see at a given redshift. So when Webb shows you more bright massive galaxies at redshift 7, 10, 14 than many models predicted, it's effectively saying your assumed expansion history plus your structure growth recipes might not be the full story. One of the leading ideas to try to fix the Hubble tension is exactly what we hinted at earlier, some form of new physics at early times, like early dark energy. The idea is simple in concept. You add a component that behaves a bit like dark energy for a short window in the early universe, changes the expansion rate back then, and then fades away before it can mess up late-time observations. That can raise the Hubble constant inferred from early universe data, bringing it closer to the locally measured value, at least in principle. But here's the catch. If you change the early expansion rate, you also change structure formation. You change when and how many dark matter halos collapse, which changes how many galaxies you expect to see at high redshift. That's where JWST's galaxy counts come in as a consistency check. If a given early dark energy model helps fix the Hubble tension but leads to too few halos and too few massive galaxies at redshift 8 to 10, and JWST is clearly seeing a lot of them, then that model is in trouble. On the other hand, if some tweak to the early expansion helps both with the Hubble constant and with producing more early structure, then it survives to the next round. So can JWST actually break this deadlock? Can it tell us whether the universe is really expanding wrong in our models? On its own, probably not, but in combination with other probes, it has real leverage. Deep fields give you the abundance of galaxies as a function of mass and redshift. Gravitational lensing with JWST can measure the mass distributions in clusters and along the line of sight, which is sensitive to how structure grew. In the future, Webb can also contribute infrared observations of certain kinds of supernovae at higher redshifts, helping to tie local distance ladders into earlier epochs. As you stack all those datasets together, you can start to ask sharper questions. Does one single expansion history with one single value of the Hubble constant fit the cosmic microwave background, the local supernovae, and the JWST early galaxy counts at the same time? Or do you need extra knobs? Early dark energy, modified gravity, something else to keep the whole story consistent? Here's the part that you should say very clearly for your viewers. If H0 is off, even by what looks like a small amount, you are not just changing one number on a slide. You are changing the whole time axis of the universe. Tweak the Hubble constant and you tweak the age of the universe today, the age of the universe at every redshift and the relationship between redshift and distance. That feeds back into everything we've been talking about, how old a galaxy is at a given redshift, how much time it had to grow, whether its mass is shocking or just aggressive. So when people argue about the Hubble tension, they are not fighting about a minor decimal place. They are arguing over the clock the entire cosmic story is written on. JWST, by revealing how much structure already exists early on, is now part of that argument. It can't solve it alone, but it can absolutely tell us which proposed fixes survive contact with the real high redshift universe and which ones don't. And here's the next escalation. If you admit that your global expansion story might need adjustments and your structure formation recipes clearly need upgrades, you have to test your entire simulation toolbox against this new universe. That means taking the huge, expensive galaxy formation simulations that were tuned before Webb and seeing where they now fail hard. Which leads straight into the next question. When we run the universe inside a supercomputer and compare it to Webb, how often does the real universe simply refuse to match the code? And here's another twist. Webb is not just a telescope. It also hijacks other galaxies as extra telescopes, and that is how it reaches some of the faintest, most distant objects you'll ever hear about. Start with the basic idea. Gravitational lensing. When you have a massive cluster of galaxies sitting between us and more distant galaxies, the cluster's gravity bends space around it. Light from background galaxies does not travel in straight lines. It curves through that warped space. To you, that looks like stretched arcs, multiple images of the same background galaxy, and boosted brightness. The cluster acts like a natural zoom lens. Webb's first deep field, SMACS 0723, is a textbook case, one cluster in the foreground and behind it, dozens of lensed, distorted galaxies that would be way too faint to see without that extra magnification. That lensing effect is not small. In some cases, it can brighten a distant galaxy by a factor of 10, 100, even more, depending on how perfectly it lines up. That's how Webb can study galaxies that are both extremely distant and intrinsically tiny or faint. Without the lens, they would fall below Webb's sensitivity floor. With the lens, they pop up as elongated arcs or little mirrored copies around the cluster. So every time Webb targets a massive cluster, it's not just looking at the cluster itself, it's also fishing in the background for boosted high redshift galaxies. That magnification is a big deal for your story. It effectively extends Webb's reach. Instead of just probing the bright tip of the galaxy population at high redshift, lensing lets you peek further down the luminosity function, towards smaller, less luminous galaxies. Those are the ones that probably did a lot of the heavy lifting for reionization and early star formation. So cluster lenses are one of the main tools to test whether the too many, too soon result holds up when you include the faint end, not just the obvious monsters. But lensing does something else powerful. It lets you map the mass in the lensing cluster itself, including the dark matter. When you see multiple images of the same background galaxy or long arcs at different positions, you can work backward and ask what mass distribution in this cluster would bend light in exactly this pattern. Astronomers build detailed models that adjust the positions and masses of dark matter clumps until the predicted arcs match the real ones. Out of that, you get a mass map, a picture of where dark matter is sitting inside the cluster. Those mass maps are not smooth. They show you the main cluster scale halo plus smaller subhalos associated with individual galaxies, and sometimes even substructure beyond that. This is direct observational information about how clumpy dark matter is on small scales. It's a way to check whether the amount of substructure in real clusters matches what ΛCDM-based simulations predict. That's where the small scale tests come in. If dark matter were very warm or had properties that smooth out small clumps, you would see fewer subhalos, and the fine structure in the lensing patterns would look different. The exact brightness, shape, and position of lensed images are sensitive to these small lumps of dark matter. By fitting cluster lenses with high precision and looking for mismatches, astronomers can place limits on how much small-scale structure there is, and therefore on what kinds of dark matter models are allowed. Webb pushes this to another level because its resolution in the infrared is high and its sensitivity is deep. It can resolve thin arcs and tiny lensed galaxies that older telescopes either blurred out or missed entirely. That gives you more constraints per cluster, more multiple images, more background galaxies at a range of redshifts, and a sharper mass model. Now step back and look at the statistical side. You don't just look at one lensing cluster, you build a sample, multiple massive clusters, each with its own set of background lensed galaxies. For each field, you count how many high redshift galaxies you find behind the lens, how bright they are, and how much magnification they likely have. Then you fold in the lensing models to correct for the magnification and the effective survey area, and you reconstruct what the underlying galaxy population must look like without the lens. If, after all those corrections, you still see an overabundance of bright and moderately bright galaxies at redshift 8, 10, 12, then the too many, too soon tension is not just a fluke of unlensed deep fields, it's echoed in lensed fields as well. On the other hand, if some of the early extreme candidates turn out to be strongly magnified and intrinsically less massive or less luminous than first thought, lensing analyses can pull the numbers back towards safer territory. Either way, gravitational lenses are the calibration tools that let you stress test your galaxy formation models and your dark matter assumptions together. So in this section, the bottom line is simple. Webb uses massive clusters as natural zoom lenses to see fainter, more distant galaxies than it could on its own, and at the same time uses the distortions in those images to map out dark matter on small scales. That double use makes lensing fields some of the most valuable data Webb can take, because they connect early galaxy physics, dark matter structure, and even cosmological models in one shot. And once you realize how much gas and dark matter are moving, merging, and getting stirred up in these environments, the next question is obvious. What does all this violent activity do to the gas itself? Are we seeing calm, gentle growth, or are early galaxies already blasting out huge winds, dumping metals into space, and slamming the brakes on their own star formation in bursts and crashes? Right now, you've seen that early galaxies are massive, compact, and full of stars. But here's the key thing most people miss. All of that activity stirs the gas hard, and Webb is now showing you that the young universe had brutal weather, not calm conditions. Look at the spectra of some of these high redshift galaxies, especially the ones going through intense starbursts or hosting active black holes. The emission lines from gas are not clean and narrow. They're broadened, shifted, skewed, sometimes split. When astronomers measure those line shapes, they see gas moving at hundreds of miles per second, in some cases over 1,000 miles per second, blasting out of the galaxy. That's what we call galactic winds, huge outflows driven by supernova explosions and by radiation and jets from growing black holes. So you don't just have a galaxy quietly turning gas into stars, you have a galaxy throwing part of its gas back out into space at escape velocity. And this is happening in the first billion years, at redshifts where people used to picture proto-galaxies just gently assembling. Webb's line profiles are telling you, no, the gas is already in full storm mode. Now think about where that outflowing gas is going. It doesn't vanish. It slams into the space between galaxies, the intergalactic medium, dragging metals and dust with it. Remember, those heavy elements were made inside stars, then released by supernovae. When galactic winds carry that enriched gas into the IGM, they're seeding the future. They're spreading oxygen, carbon, silicon, iron, and dust grains into regions that will later collapse into new galaxies and new generations of stars. That means the IGM is not just some clean, untouched reservoir, even early on. It's getting polluted patch by patch by these winds. When you fast forward, the next round of galaxies forming out of that pre-enriched gas can cool faster, form stars more efficiently, and build structure differently than if everything stayed chemically pristine. So feedback from one generation of galaxies literally preps the raw material for the next generation.
Here's another piece Webb adds. Star formation in these early systems doesn't look calm and steady. It looks bursty. Some galaxies show signs of very intense recent star formation, then the spectra and colors suggest it drops, then possibly ramps back up. Feedback is one of the main suspects. When you get a big burst of star formation, you light up tons of massive stars at once. They explode as supernovae, they inject heat and momentum into the surrounding gas, and for a while, that can blow gas out or heat it so much that it can't collapse into new stars. So you get an on-off cycle. Gas flows in, cools, star formation spikes, feedback kicks in and partially clears or heats the gas, star formation drops, gas slowly recollects, and the cycle repeats. Webb's observations of high equivalent width emission lines, combined with underlying older stellar populations in some galaxies, point to this kind of stop-and-go behavior being common, not rare, at high redshift. To really understand that, you have to know how much gas is actually there in the first place. Webb contributes here too. By looking at emission lines from hydrogen and other elements, plus the continuum light from stars and sometimes dust, astronomers can estimate gas fractions, roughly what fraction of this galaxy's baryonic mass is still in gas, not yet in stars. For many early galaxies, those gas fractions are huge. The system is still dominated by gas, not by stars, which makes sense for a young universe, but it also means there is a ton of fuel ready to be turned into more stars if feedback allows it. High gas fractions plus strong feedback and high star formation rates is a volatile combination.
You get galaxies that can, in principle, double their stellar mass in a short time if things are quiet, but that rarely stay quiet. Every big burst plants the seeds of its own slowdown through winds and heating. Webb is showing you both sides, the huge gas reservoirs and the signatures of gas being thrown out or stirred up. All of this has a direct impact on how we model galaxy growth. In simulations, feedback from stars and black holes is implemented through recipes, subgrid models that say how much energy you inject, how you heat or kick the gas, how that affects star formation. Before JWST, a lot of those recipes were tuned using lower redshift galaxies. Now, we have to ask, are those same settings valid at redshift 8, 10, 12, in galaxies that are smaller, denser, more gas-rich, and living in a harsher environment? If feedback at high redshift is more efficient than we thought, that could help explain why some galaxies stay small, or why certain extreme candidates turned out to be less massive when reanalyzed. If feedback is less efficient or couples differently to the gas, that could help explain why we see such high stellar masses and star formation rates early on. Either way, the violence of these outflows and the gas fractions Webb is revealing become key tuning parameters for simulations. You can't just dial in feedback arbitrarily anymore. You have to match the observed winds, emission line widths, metallicity of the IGM, and the bursty histories suggested by Webb data. So the picture that emerges is not a gentle, linear buildup of galaxies. It's a universe with wild weather from the start. Gas streaming in along filaments, piling up in small, dense galaxies, being turned into stars in huge bursts, and then being blasted back out in winds that enrich and reshape the space between galaxies. And once you see that, the next step in the story becomes obvious. To really understand how all of this fits together, you can't just stare at cosmic dawn in isolation. You have to stitch it into the full movie, from the very first light at redshift 15 and above, through reionization, all the way down to the peak of star formation a few billion years later. Up to now, you've been looking at pieces of the story, single frames, single galaxies. But the real question is, how does all of this line up on one clock, from the very first light to the era when the universe is making stars at its maximum rate? Start at the very earliest phase we can realistically talk about with Webb, what people call cosmic dawn. That's roughly redshift 10 to 15 and beyond, the first few 100 million years after the Big Bang. This is exactly the regime JWST is opening up, with objects like JADE's ZS14-0 and other ultra-high redshift galaxies, plus candidates that might even push beyond redshift 15 in the next few years. At cosmic dawn, the galaxies you see are small, compact, and extremely active relative to their mass. Their light is heavily redshifted into the infrared, which is why older telescopes mostly miss them. Webb's deep fields and lensing programs are now mapping how many of these first-wave systems there are, how bright they are, and what their spectra look like. Are they extremely blue, hinting at very hot metal-poor stars, or already enriched and dusty? That tells you how quickly the very first stars polluted their surroundings and how fast tiny fluctuations in density grew into real galaxies. Then you move forward a bit in time into what you can call cosmic morning, redshift around 6 to 10, a few 100 million to about 1 billion years after the Big Bang. This is the era where galaxy numbers and masses ramp up fast, where reionization is underway or close to finished, and where the universe is clearly transitioning from mostly neutral hydrogen fog to mostly ionized and transparent. This is also where Webb finds a ton of structure, with disks, clumps, mergers, and outflows very common. In this range, you're not just seeing the first light switch on, you're seeing the universe turn into a busy construction zone. Galaxy mass functions steepen, meaning there are more and more galaxies across a wide range of masses. Star formation rates in many systems are in the tens to hundreds of solar masses per year. The intergalactic medium is being hammered with ionizing photons. JWST spectroscopy in this era lets you measure star formation, metallicity, dust content, and ionization all at once, so you can actually watch reionization wrap up and chemical enrichment accelerate. Now jump further ahead to what's called cosmic noon, redshift around 2, roughly 3 billion years after the Big Bang. This is outside JWST's earliest niche, but not outside its reach. Cosmic noon is when the universe hits its peak star formation rate per unit volume. On average, galaxies are forming stars much faster than they do today. Many of them are big, gas-rich disks and violent mergers with huge reservoirs of cold gas still available. Starburst galaxies and active black holes are common. Here, Webb acts differently than Hubble. At redshift 2, a lot of the star formation is hidden in dusty, infrared bright galaxies that are faint or even invisible in optical light. Hubble can miss the true power of those systems. Webb's infrared sensitivity lets it see straight into that dust, so it can measure how much star formation is really happening at cosmic noon. That way, JWST links the early, compact, high-redshift galaxies you've been talking about to the more massive, dusty, highly active galaxies that dominate a few billion years later. So how do you stitch all of this together into one continuous timeline instead of a pile of disconnected snapshots? On the earliest side, you have the cosmic microwave background, giving you a perfect image of the universe when it was about 380,000 years old, with tiny fluctuations in temperature that trace tiny density differences. On the later side, you have Hubble, ground-based surveys, and other telescopes mapping galaxies and structure from redshift a few down to today. Before JWST, the region between the CMB and the earliest clearly detected galaxies was a big gap. JWST is filling that gap. The ultra-high redshift galaxies at Z10 to 15 connect directly to the growth of the first halos predicted by ΛCDM, starting from those CMB fluctuations. The galaxies at Z6 to 10 connect into the era where Hubble started to see galaxies, but without the spectral detail and infrared reach. Then JWST's work at Z2 to 3 on dusty galaxies and black hole growth ties into the cosmic noon era that other telescopes mapped in different wavelengths. The point is, you can now draw a line from here are the initial conditions to here is the first light to here is the peak of star formation without a missing chunk in the middle. The next step is to turn that line into a real growth curve. You take galaxy mass functions at different redshifts, basically how many galaxies exist at each mass at this time. You combine that with star formation histories derived from spectra and colors, which tell you how fast those galaxies are building new stars at each epoch. You add metallicity evolution, how the fraction of heavy elements in gas and stars increases over time. And you mix in information about gas fractions, dust, and black hole activity. Put all of that together and you can ask very hard questions. At each point in time, does the amount of stellar mass we see match the integrated star formation history up to that point, once you factor in the stars that have died? Does the buildup of metals in galaxies and in the intergalactic medium match the number of stars formed? Does the distribution of galaxy masses and sizes fit what you would get if you start with CMB fluctuations and evolve them forward with a given cosmological model and a given set of feedback rules? If the answer is yes everywhere, your model survives. If the answer is no at cosmic dawn or at cosmic morning or at cosmic noon, then the growth curve bends differently than you expected. JWST's job in this bigger picture is to lock down the high redshift part of that curve so tightly that you can't just hand wave it away. It forces every proposed cosmology and every simulation to pass a data check at multiple times, not just at the comfortable later epochs we were used to before. And when you look at that full curve from the CMB through JWST's early galaxies through cosmic noon, another question starts to press in. Are the initial seeds themselves exactly what we thought they were? Or is there already a hint in how much structure appears how early that the original pattern of fluctuations laid down in the very early universe might have been slightly different or slightly more powerful on small scales than our simplest inflation models predict? Here's the uncomfortable question behind everything you've seen so far. If galaxies, black holes, and structure are turning up this early and this strong, did we start from the exact initial conditions we think we did? Or were the seeds of structure already tilted in a way our simplest models didn't expect? Go back to the very beginning, before galaxies, before atoms. In the standard picture, the universe went through a very short, very fast expansion phase called inflation. During that phase, tiny quantum fluctuations in the energy density got stretched to cosmic scales. When inflation ended and the universe went back to normal expansion, those frozen-in fluctuations showed up as slight overdensities and underdensities in matter. Over billions of years, gravity amplified those small bumps into everything we see, from galaxy clusters down to individual galaxies. We actually see a snapshot of those initial bumps in the cosmic microwave background. The small temperature variations in the CMB are a direct map of density fluctuations when the universe was a few 100,000 years old. With that map, we can reconstruct the power spectrum of those fluctuations, basically how strong the variations are on different length scales. In the simplest inflation models, that power spectrum has a very specific, smooth shape, and the fluctuations behave statistically like a perfect random field, with no special preferred spots, what people call Gaussian. Now, put JWST into this context. If the seeds were exactly what the simplest inflation models say they were, and if you evolve them forward with standard ΛCDM plus normal galaxy formation physics, you get a prediction for how much structure should exist at redshift 7, 10, 14. You can ask how many halos of different masses form, how many galaxies they host, and how bright those galaxies should be on average. When Webb then goes out and counts real galaxies at those redshifts, it's effectively testing how much small-scale power those initial fluctuations had. If you see too much structure too early, meaning more massive halos and more luminous galaxies than expected, you can respond in a few ways. You can change the galaxy physics, making star formation more efficient or feedback less suppressive. You can tweak the expansion history with something like early dark energy. But you can also ask a deeper question. Did the initial fluctuation spectrum have more small-scale power than the simplest models say they did? That's where people start talking about mild deviations from the basic inflation setup. Instead of a perfectly smooth, slightly tilted power spectrum, you might have extra power on small scales, maybe because inflation was not a single featureless phase, but had minor changes in its behavior. That would mean slightly stronger initial clumping on small scales, making it easier for halos to form early and for galaxies to assemble faster. If JWST's early galaxy abundance really stays high after all the careful checks, that's one way to reconcile the data. You make the seeds a bit more grainy on small scales. Another direction people explore is non-Gaussianness, which just means the initial fluctuations are not a perfectly simple random field. You can have a distribution where extreme overdensities are a bit more common than in a pure Gaussian. That makes rare, high-density peaks more likely, which then act as the first sites for early, massive halos. Subtle non-Gaussian features can show up in higher-order statistics of the CMB, and constraints from Planck and other missions are already tight, but small deviations are still allowed. JWST's early galaxies add a new angle, because they test whether there are enough rare peaks early on to match the observed abundance of big systems. Here's how to explain it clearly. The CMB tells you about the seeds on large, mostly linear scales. JWST tells you how those seeds evolved into halos and galaxies on smaller, nonlinear scales, where gravity, gas, and feedback all interact. If your inflation model and ΛCDM parameters are correct, you should be able to use the CMB to predict both the large-scale structure we see today and the early galaxy counts JWST is measuring. If you can't fit both at once, something in the chain is off, either the initial conditions, the cosmology, or the galaxy physics. This is why people talk about complementing the CMB with JWST instead of replacing it. The CMB locks in the starting pattern of fluctuations at large scales and early times. JWST measures one outcome of evolving that pattern, specifically the galaxy population at high redshift, in regimes where nonlinear growth, cooling, and star formation matter. If you try a more exotic inflation model or a slightly different power spectrum, you have to check it against both datasets. You don't get to pick one. And here's the key point to make for viewers. If the seeds were even slightly different, everything changes. A bit more small-scale power and you get earlier and more abundant small halos, more early galaxies, maybe a faster route to reionization and early massive black holes. Less small-scale power and you struggle to form enough early objects, and some of what JWST is seeing becomes very hard to explain. Change the statistics of the fluctuations and you change where and when the first big structures appear, which shifts the whole growth track of the universe. So when cosmologists argue about whether JWST is seeing too many early galaxies, or whether simulations can catch up by just tweaking feedback and star formation recipes, they are not just playing with code. They are testing whether the initial conditions laid down in the first fraction of a second after the Big Bang were really as simple as we hoped. If they were not, then inflation itself, or whatever process replaced it, might need a more complex story. And that leads straight into the next pressure test. Once you think you have a set of initial conditions, a cosmology, and some galaxy physics that might fit, you don't stop at theory. You run it in a supercomputer, generate a full fake universe, and compare it to what Webb actually sees. The next question is simple and brutal. When we run our best simulations and put them up against JWST's data, how often does the real universe refuse to match what the code spits out? Right now, there's a very simple sanity check hanging over everything. If our theories are right, and our guesses about star formation and feedback are right, then when we run the universe inside a supercomputer, it should roughly look like what Webb is seeing. So the natural question is, does it? For years, cosmologists have been running huge simulations like Illustris TNG, Eagle, Fire, Simba, and others. These are not little toy codes. They track billions of particles of dark matter and gas in big volumes of space. They follow gravity, gas cooling, star formation, supernova explosions, and black hole growth. They were tuned mostly before JWST, using data from Hubble, ground-based surveys, and the cosmic microwave background. The goal was to get a universe that, at low and moderate redshift, matches the galaxy population we see today, in terms of masses, sizes, star formation, and clustering. When people started stacking JWST's early deep field results against those simulations, some clear gaps showed up. The simulations generally underpredicted how many massive galaxies exist at very high redshift. They also tended to produce star formation rates that were lower than what some JWST galaxies seem to be hitting at redshift 7, 8, 10. And when you look at reionization timing, some of the pre-JWST models had a slower buildup of UV output than what Webb's early ionized bubbles suggest. That doesn't mean the simulations are useless. It means they were tuned to a dataset that did not include the cosmic dawn regime. They were mostly calibrated to match z equals 0 to 3 with loose constraints at z greater than 6. JWST is now saying, okay, take that same setup and tell me what you predict at redshift 10. And the answers don't always line up. So the next move is obvious. You retune the physics that happens below the resolution of the simulation, the so-called subgrid physics. That includes the rules for how gas turns into stars, how strong supernova feedback is, how black hole accretion and jets heat gas, and how efficiently radiation couples to the interstellar medium. In a simulation, you can't resolve every star or every supernova. You have to use effective recipes. Pre-JWST, those recipes were set to match the galaxy population later on. Now, people are exploring versions that allow more rapid early star formation or different feedback behavior in small, dense, high redshift galaxies. You can crank up early star formation efficiency. You can allow gas to cool faster in low metallicity environments. You can tweak how easily gas is blown out of shallow potential wells. You can also adjust how quickly black holes grow in tiny galaxies and how much energy they dump back. The goal is to see if, within the same ΛCDM cosmology, you can produce more early massive galaxies and higher star formation rates without destroying the match to the lower redshift universe. On top of that, new JWST aero simulations are being run specifically to compare with Webb surveys, not just in a general sense, but object by object and statistic by statistic. Teams now take the outputs of their simulations, make mock observations using JWST's filters and noise levels, and then build fake catalogs that look like JADES, GLASS, or HUDF. They then run the same selection techniques and photometric redshift codes on the simulated data that observers use on the real data. That way, you can ask a clean question. If my model universe were real and I pointed JWST at it, would I recover a galaxy population that looks like the actual catalogs, or not? Some runs are already getting closer, especially when they allow aggressive early star formation in dense halos. But there are still tensions, especially at the extreme bright, high redshift end. In a few cases, even with optimistic assumptions, simulations struggle to produce enough JADES GS-Z14-0 type objects in the volumes probed. In others, they reproduce total star formation density at high redshift only if they push feedback in ways that then cause mismatches at later times. There's a constant trade-off because the same physics that boosts early growth might overshoot at cosmic noon or at low redshift if you're not careful. This is where you want to be blunt with your audience. When the code fails, that's not embarrassing, it's valuable. A mismatch between a serious simulation and Webb's data is not a bug to hide. It's a signal that some piece of the physics or some assumption about initial conditions or cosmology is wrong or incomplete. Maybe star formation in low metallicity gas is more efficient than we modeled. Maybe feedback couples to compact early galaxies differently than in big disks. Maybe black holes in the smallest halos grow faster than we expected. Or maybe the underlying cosmological model needs a mild tweak in its parameters or early time behavior. What you do not get to say anymore is we can make anything match by just turning knobs, because Webb gives you many knobs to match at once, not just one. You have to simultaneously explain early galaxy counts, star formation histories, metallicity evolution, reionization timing, and the later universe. Simulations that pass all those tests are rare, and that's exactly the point. The bar is higher now.
So in this section, the takeaway is simple. JWST is forcing simulations to grow up. The old pre-JWST runs were good enough for a universe where the first billion years were mostly blurred out. In the new era, where we're seeing actual galaxy populations at Z10, 12, 14, the code has to earn its keep. When it can't, that's where the real progress happens, because you know exactly where the physics is hiding. And there's still one more layer of pressure to add. Even after you've tuned simulations and tweaked models, there are things Webb still hasn't shown us, cases that would be absolute smoking guns for new physics or for the very first generation of stars. So the last question you need to raise is, what are we still missing in this picture? And what are the next discoveries that could force us to rewrite the story one more time? Even after everything you've seen in this story, there are still a few pieces missing, and they are not small details. They're the kinds of discoveries that would slam the door on whole debates or blow them wide open. Start with the big one everyone wants, a clean detection of true population 3 stars. Right now, all of our first stars talk is based on theory and indirect hints. We have models that say the first generation of stars formed out of pure hydrogen and helium, with no metals at all. Those stars should be very massive, very hot, and very short-lived. They should leave distinctive fingerprints in the spectrum of their host galaxies, but Webb has not yet delivered an unambiguous, no-wiggle-room detection of a pristine population 3 star cluster. Instead, what we have is a bunch of almost cases, galaxies at high redshift with extremely low metallicity, very blue spectra, and line ratios that suggest very hot stars. They're close, but they still show some trace of heavy elements, so they're not truly first generation. JWST surveys like JADES are actively targeting candidates that look as primitive as possible, pushing deeper, looking for extremely faint, extremely blue systems with basically no metal lines at all. The moment we catch one, it's a direct look at star formation before any chemical pollution, and it would lock down how the first lights in the universe actually behaved, instead of just how we think they behaved.
Then you have the frontier in redshift itself. Right now, we're talking about secure galaxies out to around redshift 14. That's already insane compared to the pre-Webb world, but in principle, there's room to go further. If you push deeper with longer exposures or use gravitational lensing clusters to magnify the background, you can reach galaxies whose light left them maybe 200 million years after the Big Bang, or even a bit earlier. Those would be systems at redshift 15, 16, maybe higher. There are already a few very high redshift candidates in the literature that sit on the edge of that territory, but many still need solid spectroscopic confirmation. The data is hard, the objects are faint, and the risk of contamination is real. Over the next few years, deeper programs will keep stacking exposure time on the best fields, and lensing surveys will keep scanning behind massive clusters. Every new ultra-high Z confirmation shrinks the gap between the cosmic microwave background at 380,000 years and the first galaxies, and narrows down how fast nothing turned into a functioning galaxy population. Now, zoom out and look at the bigger timeline of instruments. JWST is not going to be alone. NASA's Nancy Grace Roman Space Telescope is coming, with a massive wide-field infrared camera. Where Webb gives you incredibly deep, narrow pencil beams into the universe, Roman will map huge areas of sky at high resolution in the infrared. That combination is lethal for cosmology. Webb finds and characterizes the rare extreme objects and the detailed physics in small patches. Roman will give the big statistics, the large-scale patterns, the weak lensing maps, and the supernova samples that pin down dark energy and dark matter over enormous volumes. On the ground, extremely large telescopes like the ELT, the Giant Magellan Telescope, and the 30-meter telescope are being built with huge mirrors and advanced spectrographs. They will be able to take spectra of fainter galaxies and at higher resolution than we can manage now, especially at somewhat lower redshift, where ground-based infrared works well. Think of them as follow-up machines that can dissect individual galaxies Webb finds, measure dynamics, resolve star-forming regions, and push chemical abundance measurements to the next level. All of this loops back into refining the actual numbers in our cosmological model. JWST's galaxy statistics at high redshift feed into constraints on basic parameters like the Hubble constant, the matter density, and the details of dark energy. You combine CMB data, baryon acoustic oscillations, supernova distances, and now high redshift galaxy abundances and lensing with Webb. If they all point to the same parameter set, cosmology looks solid, even if the galaxy physics inside that framework needs work. If they don't, you know exactly where the model is failing. That's the real endgame here. You're not just counting pretty smudges. You're tightening the error bars on the fundamental numbers that say how fast the universe expands, how much matter it holds, how clumpy that matter is, and how the expansion rate is changing over time. Webb's early galaxies are already being folded into big joint analyses that ask, given all of this, what ranges of H0, omega matter, and dark energy behavior are still allowed? As more data comes in, the allowed region in that parameter space shrinks. So where does that leave you? The line you want to land on is simple. We built Webb to see the first galaxies, to finally turn that blank early chapter into images and spectra. It did that, but it also did something more dangerous. By showing you that the early universe is full of bright, massive, chemically active, dynamically violent galaxies way earlier than expected, it is forcing you to reconsider almost every step of the story, from how the first stars formed, to how black holes grew, to how fast structure assembled, to whether the basic cosmological model needs extra ingredients. In other words, the telescope that was supposed to quietly fill in a missing piece is now leaning on the whole picture. The first galaxies are here, they are real, and they are loud. Now the theory has to catch up. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.